Hello everybody, this is Dr. Young, and in this video I'm just going to introduce to you the idea that we have a bunch of additions to carbonyls that are totally reversible, easy to undo, and I just want to compare it real quick to the irreversible additions that we've learned so far to aldehydes and ketones. So we just came off of, these other additions to these aldehydes and ketones, where we just added things to them. Some of these are reductions, some of these are oxidations, but we just added something to a molecule, right? So like, for example, in this first one, you just added a hydride, right? So your sodium boryl hydride just attacked this went up, picked up an H from the solvent somewhere, and we ended up adding an H here and an H here. And this reaction, it's not super reversible. You just added something to it. It's not like it didn't have any reversible steps in it. It requires a completely different reagent, a high energy reagent, to turn it back to the original ketone, right? You'd have to oxidize it with some unstable oxidant. So these things just don't slide backwards, right? They don't just fall apart on you. If you look at the second one, we've got the Grignard, right? So the organometallic one, that in this case magnesium, where we had this attack, right? You treat this carbon like it's negative. It does the same thing, attacks carbonyl, kicks up, yada yada, so that you've got OH, and then you've got an ethyl group. Same thing, real stable molecule, not going to fall apart and form the parent ketone very easily at all. Again, you'd have to do a whole bunch of work. This one would be way harder because you've got a carbon and not a hydrogen that you attached. And then there's the Bear-Villiger. I use MCPBA in this example, where again, in this case, if you added MCPBA, your major product should look something like this. You got 3 carbons coming off, right? 1, 2, 3, yep. And again, not easy to turn back into the parent ketone. You'd actually have to do quite a bit of work to turn that back into the parent ketone. So these are examples of irreversible additions to aldehydes and ketones. This next big section here is going to talk about 5 different new functional groups that are super reversible. Some of them are so unstable that we barely see them, or they're constantly in a dynamic equilibrium. And so let me show you what those 5 are. So let's take a look at the first one, which is just the hydrate. And we've actually talked about this when we were talking about oxidations, where we said, oh, well, if you have water present around a carbonyl, there is an equilibrium that forms where you form what's known as the hydrate, right? Which is where you turn that carbonyl into 2 OHs, right? So, all right, hydrate, also sometimes called a geminal diol. And like we mentioned before, it's not like the water adds to it and then just sticks. It's very, very reversible. It's just an equilibrium, right? This really should just be an equilibrium arrow because these things are unstable. I'll put that as a star here, right? These are unstable. Nobody's going to hand you a bottle of hydrate, an organic hydrate. They're just too unstable. Formaldehyde forms like a fairly decent hydrate in terms of stability, but most other things, the equilibrium lies way, way, way on the carbonyl side, on that keto side or enol or aldo side. So you're not going to see a lot of hydrate out there. It's just going to be a small percentage of what that organic molecule looks like when you have it in the presence of water. I'll show you the mechanism in a future video, but unstable tends to just go back to the carbonyl. But we also have the acetals and hemiacetals here. So if I replace water with instead some sort of alcohol, right? So this is an alcohol, and I'll put here 1 equivalent. And oftentimes we catalyze these with acid. You may or may not need acid to do it, but sometimes you'll see this formed. You can form what's called the hemiacetal, which is, and let me draw this so you can see the addition piece a little bit better. Right, so here's the original O. And then with that alcohol added, now you've got a hydrogen on there, and then you've got an OR group on there. And so when you have a carbon with an OH and an OR group, right, an ether on it, that's what we call the hemiacetal. Hemiacetal. And these are also unstable. So they just sort of automatically fall back apart. They just automatically just kind of gonna go back to being the parent carbonyl. We'll talk later when we talk about carbohydrates, that carbohydrates actually form hemiacetals, but again, it's reversible because a carbohydrate like glucose, you may have heard for some of you who've had biology before, that glucose can be in like a straight chain or an open form. And then it can close to form either alpha glucose or beta glucose, and those alpha and beta are talking about how do the hemiacetal form. But the hemiacetal form is not stable. It opens back up and it closes and it opens and it closes. And that's because, again, hemiacetals are just not stable. Now, a full acetal is stable. So if I have an alcohol, but now I have 2 equivalents at least, or excess, and here I do definitely need H plus as a catalyst to help me form this. What I can do is, instead of having an OH and an OR, I end up with 2 ORs. And so that carbon with an OR on one and an OR on the, or sorry, you have 2 ORs or 2 ethers on the same carbon. That's what you call the acetal. And that is stable. So now we finally have one of these that is stable and will hang out. You can go buy something in its acetal form. You can protect a molecule and make an acetal and have it just stick around. And that's because these ethers are really stable. They're not going to just unravel on you magically, but they are very, very easy to reverse, which is why we're putting it under this reversible addition part. Now, those are all involve oxygens, right? We added water. They all involve oxygens here, but you can do this with nitrogens too, right? So if we have a primary or a ammonia, so I'll put ammonia here, so NH3, or a primary amine. Then what we can do is, and actually maybe I should take a little side note here. So here's a little side note, just to make sure that you're understanding primary, secondary, etc. If you look at this, right, so types of amines, if you have, let's say, this amine, or this amine, or maybe that amine, right, you can use these terms, primary, methyl, or primary, secondary, etc., with amines also. It's just referring to how many carbons are coming off of that nitrogen. So since in this first example, I have 2 carbon groups coming off of that nitrogen, this would be a secondary amine. On this one, since I only have 1 carbon group coming off, that would be a primary amine. On this one, since there's just 3 methyl groups, that would be a tertiary amine. And on this last one, again, I have 2 carbon groups, so that would form a secondary amine. So in this example up here on this reaction, when I'm talking about ammonia or a primary amine, I mean I can only have 1 R group coming off of it, right? So I can have an R group with an NH2. And these usually also have an acid catalyst. So I'll put an H+. And what you're going to form if you take a primary amine and acid and you react those with a carbonyl is you're going to get what's called an imine. So N double bond, and I'll put R here. It would be a hydrogen if you used ammonia, but R group, it would be that R group if you used a primary amine. And this is our imine, I-M-I-N-E. And these are also stable. These can form and you can keep them. You can bottle them up and you can ship them out and you find them in drugs, etc. So these are stable. This would be called an imine, where you have a C double bonded to an O. And then if you have a secondary amine and acid, you can form our last one. So secondary amine and acid, so something like, right, some R2 and H. Then you're going to form what's called an enamine, where the enamine is where, it's kind of like an enol, where an enol is where you have an alcohol on an alkene. An enamine is when you have an amine on an alkene. So in this case, you're going to get your amine here, which has the 2 R groups, but notice that you can't double bond this nitrogen because it's already got 2 R groups on it. So what instead happens is you get this elimination here. You get a double bond on one side of those things. And this would be what's called an enamine. An enamine, and these also are stable. So these are the kind of the 5 different really, really easily reversible additions to carbonyls that we're going to talk about. The hydrate's really, really unstable. It just falls apart automatically. Same thing with the hemiacetal. It's really unstable. It falls apart automatically. And then for the acetal, imine, and enamine, they're very easy to reverse, very, very fast, very, very easy. All you have to do to reverse any one of these is to simply add acid and water. So I'm just going to put H3O+, H3O+, and the reverse for this one, I don't know where I'll draw it here. H3O plus. Right, so you just add a little acid and water and it reverses back to that parent, in this case, ketone, super quickly, super easily. Anytime I protect something with an acetal and I go to take it off, I add a little bit of acidic water to my solution. I go to take a TLC within the first 10 minutes, it's gone, it's done, it's totally gone back to the parent carbonyl. So it's very easy to reverse. You don't need high energy reagents or anything to undo anything. But so what I'm going to do in these next videos is talk about in a little bit more depth. In one video, I'll talk about the hydrate and hemiacetal and acetal stuff. In another video, I'll talk about how do you make the amines and enamines. And then I'll do one more video on how we use acetals in particular as protecting groups to protect ketones and aldehydes from reacting in ways that we don't want. So go ahead and start looking out for parts 2, 3, 4, and 5. Okay, happy studying. Take care.